My name's Peter. I apologise for any of you who actually bothered to scan that QR code and you were all rickrolled. You can admit it now. Um, there are actually genuine, sensible QR codes throughout the talk, though, so I'll try and put them up. So if you actually have questions about anything, that's your opportunity to jump in. I'm also going to point out the fact that I'm an engineer. I'm not a public speaker, and therefore they don't let me out the back room very often. But unfortunately, none of the good speakers are here today, so you got me instead. And one piece of advice I was once given when on public speaking is whatever you do, don't include any equations or graphs. And the rest of the talk has no equations or graphs, but unfortunately, ever the contrarian, I thought I'd get those out of the way. And then third, and you've already had the intro, but I should say who I am. My name's Peter. I'm a academic, and I've also started a couple of companies, which one of which is Exobotics. And most of the talk today is going to be from the point of view of Exobotics, but I'll try my best to make sure it's not too much of a company promotion spiel. Instead, it's informative, and yeah, everyone gets to learn some cool things about satellites because I didn't know any of it a few years back. So I'm going to skip through that. I also owe a shout out to these amazing people. These are my co-founders at Exobotics. I met most of them at uni, and they're some of the most talented people I've ever had the pleasure of working with. The first of these is Nadim Gabani, moody mastermind, design wizard. And then there's Maxime Bagance, who's our clean room master, and then there's Shveta, who's our business magnate. Yeah, and without them, they're the real heroes of the story. So the plan for today's talk is really, really simple. I want to start with a taster session for space and why it's cool. But given that you're all members of the Open University Space Society, I suspect that you're not going to need too much convincing there. We'll then go on to talk about some of the design constraints of working in space. If you're anything like me, one of the best parts of playing a video game is finding out how to make broken builds, and space is like that. A bunch of unusual rules that combine in unexpected ways to give cool and sometimes very difficult things. I beg your pardon. We will briefly restart. We'll then take a quick break for questions. This is also an opportunity for anyone who's bored to sneak away, anyone who bought rotten fruit and vegetables to post it to me. And then after that, we're going to jump on to a brief discussion of some of the implementation challenges that we'll meet. We'll talk about a couple of the missions Exobotics is currently working on, and we'll also talk about Pringles cans, Moxies, and the meaning of life. And then there's more questions and an opportunity for people to throw away any remaining rotten vegetables they haven't already put in the post. So let's start with some context. You've probably all seen this thing in the news a lot, but if you haven't, this is the James Webb Space Telescope. Bits of it were manufactured in the UK. I'm not sure which universities and towns and cities are represented here today, but I know a number of the mirrors were created in Cranfield near Milton Keynes. And this is one of the most high-tech pieces of engineering ever built. And it cost about $10 billion and also takes some incredible photos. For example, this is the Southern Ring Nebula from the James Webb on the right and Hubble on the left. Sorry, wrong way around. And this overlay really shows the difference in quality between the two that can be achieved in only a few decades. And one of the things that's really unique about James Webb is it's sat at what's called a Lagrange point, L2 to be precise. And there's a number of reasons for this, but the most key is that this has the effect of being a local flat point of gravity in the Sun-Earth system. So that's here. And the key point, though, is it's not actually sat in the Lagrange point, no, it's orbiting around it while it orbits around the sun. And the Lagrange point has the effect of being like another body that you can orbit around. And it has the effect of keeping James Webb always pointing away from the sun, which obviously is what you need because you don't want the background of light. And I like this picture a lot because it shows the temperature difference across the back of the satellite. And as we'll come to talk about a little bit later, temperature is actually one of the real killers in space, and it can be some of the most interesting challenges come from how we handle it. Unfortunately, nothing I've ever done or I'm going to talk to you about today is nearly as exciting as the James Webb Space Telescope or nearly as expensive. So instead, I'm going to give you a Bildungsroman, which, with my pre-A-level knowledge in literature, means that it's a fancy way of saying it's a story of personal growth and learning new things. It's like the Lord of the Rings, starry-eyed kid finds magic sword, friendly old man, and they go to save the kingdom from the evil lord, and along the way they find out that it's all about family, that sort of thing. I also don't know how to pronounce Bildungsroman, I'm afraid, but I guarantee it isn't the way that Google thinks it's pronounced. Anyway, during my PhD in 2018, I started a company with some friends with the broad remit of doing space stuff. And over the time, that's narrowed down to building satellites. And as a result, I've got two hats here today, and both of them are cowboy hats. I've got Exobotics, which is the company, we build satellites. And then I've got my university, which is currently Nottingham, which I also do research on space, but it's more theoretical. So let's dive in to some of the constraints of working in space. And these are some of the things you won't be told if you read about the space sector, but some of the things you'll have to consider if you want to be a designer or engineer in space. And the first one of these is relatively obvious, and it's going to need the chat open for this one. This is the International Space Station. No cheating. Answers in chat, please. How much do you think it weighs? Have a guess. Going once, going twice. Any thoughts on how much you think this weighs? I was off by an order of magnitude when I wrote this talk. Okay, fine, no responses. It's 200. You're actually pretty good. 200 tons is not a bad guess. It's 420. It would be if it worked. So the first and biggest constraint is mass. And that's going to be a very big recurring question throughout today. And this is the second heaviest thing that we've ever put into space. This is the Mir space station from Russia, and it's 130 tons. Now, it's worth mentioning that the cost to put something into space in LEO, so that's low Earth orbit, is £100,000 per kilogram. So anything, and it's much, much more, like 10 times more expensive to put something into geosynchronous orbit, which is where the big satellites go. On which line? This is a Telstar 19V. It's a big comm satellite. This thing weighs 7 tons and would have cost many, many, many millions to put into space. This is a GPS satellite, which is, well, it's a rendering of a GPS satellite, which is about 1 ton. And then there's James Webb itself, which, despite the fact it's absolutely massive, only weighs 6 tons. Now, nothing that we've done today gets anywhere near to that. But the reason weight is a problem is this. I'm not going to try and pronounce the name of this equation, but this is the killer. Is because not only when you shoot rocket fuel out the back of the rocket, not only do you have to lift up the mass you're trying to take to space and the mass of the rocket, you're also having to shoot out the fuel for the mass of the next segment as well. And it leads to this exponential growth. And the point here is that this hasn't got much better in the last 50 years. The state of the art in rocket engines is still explode fuel out the back of a rocket and see what happens. And okay, it is better, and as a result, launch has got cheaper, but it's not as much as you might think. But it is changing. Okay, so the second constraint of working in the space industry is miniaturization. So when I was a kid, the talk was all about how your Nokia brick had more processing power than the Apollo flight computers. Well, I just did the maths, and I reckon if you filled a stadium with the Apollo flight computers, you still couldn't run Crisis. And as a result, while computing power has massively, massively moved on, the space industry takes a long time to catch up. We'll come back to why in a second. And there are exceptions to miniaturization. Not everything can be made smaller, one of which is lenses and mirrors due to what's known as the Rayleigh criterion. The resolution you can get out of an optical system is proportional to the size of the lens in that system, which means you still need massive lenses, even if everything else in the system is very small. It's why James Webb Space Telescope is massive across, even though its active elements are much smaller. And this probably brings us to the biggest innovation squasher in the industry, particularly for small companies, and that's flight heritage. Due to incredibly long lead times, enormous costs, and perceived risks, missions are really, really reluctant to fly new things. For example, the best rad hard computer currently, so that's a computer that's designed to withstand space radiation, is the Leon processor that was designed in the 90s. There are people on this call who weren't even alive when this was first designed. The space sector is extremely risk averse. And I'm originally a software engineer, so this is something I really struggle with because the software motto is always move fast and break things, or try it and see, but that's not very popular in space. And it's understandable given that the money is normally from the taxpayer, but it's still a major problem for innovation. And to be fair, this is something that's changing. Regardless of what you think of people like Elon Musk, the new species of space entrepreneurs have realized it's just cheaper and better to try and see. And they're normally doing this with taxpayer money still. SpaceX doesn't make money. The US taxpayer gives it hundreds of millions per year, which is, I think, interesting that I don't think space currently has a billionaire, as in a billionaire made by the space sector, as opposed to a billionaire who made their money and then came into it. And I'd be open to being corrected on this, but I can't think of anyone for this. And the reason is that space is not actually a very good fit with current commercial models, I don't think. And that brings us to reusability. And this is pretty high on the list of things that people want to know, which is why so many things not reusable. And the answer is that the extra mass brings it weighs a lot. And due to the exponential equation from earlier, means that it's typically vastly more expensive in the long term to reuse. In fact, there's a very good case to be made that reusing stuff is worse for the environment because the cost of making the metals that goes into a booster is less than the cost of the extra fuel you need to fly a heavier booster because it has the ability to absorb extra stuff. Now, again, that's changing, but for the moment, reusability is one of these things lots of companies do to talk about, and because they need faster manufacturing, but isn't actually something that's very widely spread. But again, that's changing. And like Elon Musk can land boosters vertically, and that's made a big difference. In fact, there's even a company in Cardiff that's talking about making reusable satellites and re-entering them with a parachute scheme. It'd be amazing if they managed to pull that off. And that brings us to another constraint of building and designing a satellite, which is it's very, very complex, and the time taken to develop something is very hard. So people need modularity. Now, typically, that's modularity of design, reusing designs you've used before, but the whole thing is built in one go. And from the business point of view, this means that space is a very high margin industry, even if sales volumes are very low. So you may not sell many things per year. When you do sell it, a very large percentage of that is profit that can be reinvested. Now, it's still not a good way to make money, but it does mean that the industry is quite different from other high-tech industries, like, say, making a machine tool. And there's also a lot of manual elements because there's not much point optimizing a manufacturing process if you're only making a few items a year. And this probably brings us to the best example of modularity in the space sector, which is CubeSats. So these came out in the 90s from Caltech and Stanford, and they were student projects, and they came up with this really clever scheme of where you'd be able to have a modular satellite. So the idea was you'd have it built up in boxes, and then you'd be able to slot boards into it that could work together. This is a very, very powerful tool. It allows for standardized components with standardized deployment, standardized burst, and generally faster and cheaper design. Again, with downsides on mass. And the power of CubeSats has led to a revolution in the number of small satellites. Thousands going up each year now. Like, this slide's only a couple of years old, and that 2,000 number is now up to about 6,000. And it's gone from building satellites over 10 to 20 years to something that now recently Exobotics just built one in 9 months. And it's 100 times cheaper than what could have been done very recently. Though, again, the exception is imaging, because imaging still requires the larger lenses to get better quality images. So if anyone can design me a foldable lens, you'll be a very rich person. And then this brings us to something that's probably worth being aware of about the space sector. Is this narrative is changing, but for a long time there's been this discussion about old space versus new space. The idea being that Old Space they're the big companies. They've been doing this a long time, and they're very, very reliable, but they go all the way on bureaucracy and doing it slowly and thoroughly. And then there's New Space, which is the startup-esque world, and it moves fast and breaks things. Um, and the two don't necessarily work very well together. They tend to recruit from very different catchment pools. They're very different funding models. Um, and while companies like this are working more and more together now, you will find that the way Airbus does something is incredibly different to a startup. In fact, one of Exobotics' things is that we're trying to bring the two together. We're trying to bring the reliability and quality of an old space project built over 10 years and bring it to a new space project that we can deliver in 9 months. I've told you not already. In fact, not only that, but we've also got a big focus on engineering. We're all from advanced manufacturing backgrounds of some form or another. So we've tried to bring new tools that are widely used for, say, making cars and bring that to space. And space is in quite a nice position here, is because it's still a very small economy compared to, say, automobile or just aerospace as in planes. That means there's an awful lot of very advanced technology that can be bought from other places relatively easy. So two examples here are additive manufacture for 3D printing in metals, and digital twins, the idea that you're going to have a computer version of your thing and a physical version of your thing, and the two are linked very deeply in terms of how you communicate, and it means you can test and run things in advance on your computer model before you run it in real life. And that's two things that Exobotics has lent quite heavily into. So, next constraint, we've had mass, we've had miniaturization, we've had flight heritage, we've had reusability, we've had modularity. So this is the next one, is scale. Modern space is working on huge networks. SpaceX has thousands and thousands of satellites already and thousands more to come, which unfortunately brings us to the challenge of space debris. There's currently about 5,500 active satellites in space, or at least there was when I wrote this 6 months ago, so this is probably out of date. And NORAD, so that's effectively the US military, tracks about 15,000 pieces of space debris. And the problem here is that most of this is in what we would call low Earth orbit, or LEO. And many key systems are above this. GPS is above the LEO band, as is almost everything most people have heard of, with the exception maybe of the International Space Station. And I've often thought there'd actually be a really good horror movie to write here, because um, there's a genuine risk of a chain reaction. Large satellite hits another large satellite and it breaks into thousands of small pieces. And because of Stokes' law, it means the smaller the pieces, the longer it takes to fall down. Like a large satellite in LEO will deorbit naturally from the atmosphere that's up there in only a few years. Whereas something the size of a grain of pea will take much longer, and something the size of a grain of sand could take 10,000 years. So actually, when we're talking about challenges that face the world today, there's the normal climate change, but one genuine one is we don't know what will happen if a satellite explodes in LEO. There's a non-zero chance that it causes a chain reaction, not entirely like a nuclear bomb, and you'd end up with a cloud of debris. And there's a bunch of companies who are looking into this, and there's lots and lots of interest from countries because it's quite a big risk, because it means there'd be potentially 1,000 to 10,000 year period where humans wouldn't be able to go to space. And as a result, modern satellites have much stricter requirements on their ability to deorbit, take themselves out, and their ability to do collision avoidance, and the fact that they work. Because the issue isn't the satellites that go up there and work, it's the satellites that go up there and then are broken and you can't control them. Now, while obviously that's scary, it's not that scary yet, but it is something we need to be aware of in coming years. Okay, next consideration is the environment of space. Not the environment as in plants and trees, but the environment as in what space is like as a place to put something. And the biggest ones here are temperature, vacuum, radiation, and space debris. And we've already talked about space debris, but we'll quickly touch on the others as well. So radiation is the first here. On Earth, we're surrounded by a charged field of particles called the Van Allen belt. that protects us from radiation from the sun and from space. But for satellites, particularly those in satellites in higher orbits, have to deal with thousands of times the radiation we have here. So, and that can be a killer. But probably the biggest killer is the combination of temperature and vacuum. Um, so currently, 25% of nanosatellite missions fail between launch and commissioning. That means 25% of satellites built by companies fail after they leave the launch pad. They never took home, or some variation on that. And that number goes up to 55% if they're built by universities. Because it's actually a very difficult environment. Vacuum is hard enough, but vacuum with wild temperature changes is very, very difficult. And as a result, this is actually one of the first things that we did as a company is we built a testing service for this. So if you build a component currently, it's actually very hard to test in a space environment. So we built this thermal vacuum chamber system. So it's the idea is it can go in your design office between your 3D printer and your espresso machine, and you can put your objects inside it, and then you can do a nearly 200-degree temperature range, and you can run it down to vacuum. And it has this interface. Anyway, I promised this wouldn't be a company commercial, so we'll move on. I also want to pull up another couple of environmental considerations that aren't maybe quite as obvious, and these are the launch ones. And the biggest here by far is vibration. Launch is an incredibly rough ride, and it can do a load of damage. And then a much less obvious one is helium testing. We'll come to that in a second. So for vibration, this is an example of a vibration test. Unfortunately, when I wrote this slide, I intended to come back and finish it, and apparently I forgot. So vibrations are bad. Surprising, absolutely no one. So at the end of every satellite design cycle, you'll typically put the satellite in the deployer. So it's effectively like a Pringles can with a spring in the bottom, and you kick the satellite out at the bottom. And then you put it on a shake table, and then you shake it incredibly hard. So this is one of Exobotics' ones in a shake test. And it's very scary because you treat this thing with extreme care in the clean room, and then you take it to a big table and you shake it, and it makes this horrible rumming noise as it's banged around inside the box. And yeah, it's not good for the heart. Anyway, and the second one is helium. A number of modern systems, including particularly Falcon 9, use helium for pressurization. And the reason for that is you need some kind of pressure environment inside the rocket typically, but you don't want to use anything that can combust. And you definitely not hydrogen. So helium is the go-to. And the problem with helium is because it's such a light material, it can work its way into anything. You'd be amazed by the amount of stuff in your phone, for example, that will die if you put it in helium. If you want to kill a phone, put it in a helium balloon. Your GPS will die pretty quickly. Other things, not quite so quickly. Okay, and then this brings us to possibly the biggest constraint of all, which is politics. And here's a quick question for the chat. Right answers only, wrong answers only. No cheating. Which country has the most satellites in Europe, do you think? Just guesses? No. UK. UK is a good guess. Someone may say, unfortunately, the UK isn't in Europe. Russia is definitely not in Europe. Germany is pretty good. Germany is number 2. Okay, I'll tell you. The answer is it's Luxembourg. And the reason for this is another piece of interesting fact is Rwanda recently filed for 300,000 satellites. And the reason for this is because it's space, a lot of the laws are set over from the Cold War, means that the way things were set out then was that each country effectively agreed to do their own thing. And they all promised to fix anything they broke. So in theory, at least, massively simplifying, if you're a country and you launch a satellite and that satellite crashes into the International Space Station, then the country that made the satellite, in theory, has to fix it. And as a result, this means that every country has their own licensing rules that make some of them, at least, are incredibly expensive. Now, for example, in the UK, if you launch a satellite, the chances are you'll probably spend more on getting the license and the insurance than you would on the entire rest of the mission. Whereas in a country like Luxembourg, it's much, much more lenient. Though that is a sweeping generalization. I'm not a lawyer. Please don't sue me. So you've probably all saw this in the news. It's obviously very sad that this crashed, and well, the undercarriage did, and the company's now gone bankrupt. But there's a good chance it may well stay. And the reason this is interesting is that there's a huge explosion in launch currently. There are a lot of countries trying to do launch, and the UK is one of them. We'll come back to that in a second. So politics also has a more obvious effect, is that, for example, the current conflict in Ukraine is very good for business. That's a sad fact, but the Ukraine war has been an incredibly good for business for the space sector, because a lot of space sector money comes directly or normally indirectly from the military. Increased spending in the military means increased spending in the US, at least in NASA, and that means increased investment in companies. And this always ends up being the elephant in the room in a lot of the space sector, is that vastly more money is spent on defense than is spent on anything else in the space. And this can often come in particularly surprising ways. For example, our first ever set of missions were actually delayed twice in a row because it turns out that Space Force has the right to commandeer SpaceX's launches at very short notice. So towards the start of the Ukraine war, they clearly wanted to put some stuff up quickly, and they commandeered the launch that would have had our satellites in it, and we got delayed, and then it happened again. Okay, that's a next constraint is cost. Space costs the dough. It's very expensive. Now, these numbers vary massively, but you can be expecting to spend about £100,000 per kilogram to put something in low Earth orbit. And it's probably going to cost you a similar amount to build it. And there's a reason that Elon launched his Tesla Roadster into space. A, it was great PR, but B, it was actually probably cheaper than building a satellite. And to give you an example of quite how expensive space is, here are some things that are actually cheaper per kilogram than a satellite, including solid gold, Rolex watches. In fact, this white powdery stuff is pretty much the only high street consumable that isn't more expensive. It isn't less expensive in building a satellite. Which brings us to the question I get asked the most when I tell people that I work in space. And that question is why? And it's tempting to be flippant and to say that, oh, I work in space because it's cool. And the chances are that everyone on this call probably already has an opinion about space. It's a very Marmite topic. Lots of people say we shouldn't be wasting money on that. Let's solve Earth's problems. And some people say we should be pushing advantage. And I would point out that the economic benefits of space are phenomenal. The Apollo missions famously returned about $6 to $8 per dollar invested. That's double what is like considered the gold standard for government investment. And there's a huge quantity of modern technology, from computing to GPS to Earth observation, is dependent on it. But also, I'll be honest, there is an awful lot of rich boys' toys. And a lot of people saying, oh, it would be cool to have my own satellite, and then they're paying to get it done. And that is an issue that the industry is dealing with. And it is one that's we're going to have to deal with more in the future as well. Which brings us to the next one, which is sustainability. So this is one that may actually surprise you, is that space is actually one of the greenest high-tech industries there is. And the reason for that is because everything is very high value, low volume. And a single SpaceX rocket launch costs about the same carbon-wise as a transatlantic flight. And it's getting cheaper. Space launches emit only a fraction of a fraction of a fraction of the carbon that airlines do. And again, we need to move towards carbon neutral, but actually SpaceX in terms of space in terms of emissions per pound spent is actually pretty green. And again, there is more to be done, but environmental concerns are not as big in space as you might imagine. And typically because space is also enabling a ton of things for supporting environmental change and targeting climate change. But it definitely needs work. So in the answer to the question of is space worth it, I would say yes, but there's still work to be done. We need to make sure that we give better value per pound invested, and that we're actually supporting real useful missions rather than just doing it because it's cool. Which brings us to another constraint on our list is launch. There's a massive boom in number of companies offering launch services, or rather, number of companies saying that they will be offering launch services in a few years' time. There's 160-ish at the moment worldwide, 3 of which are in the UK. And I would say there's probably only space for about 20 globally. I mean, an awful lot of companies failing. In fact, I heard a VC recently say that the best way to lose money right now is to invest in a launch company. And there's a need for more launch things. As satellites get smaller, it gets harder and harder to fill up the payloads of larger rockets. It takes potentially years to fill a Falcon Heavy with CubeSats. It just can't be done. So Orbex in Scotland, for example, is trying to make a 19-meter long rocket. But it's hard to make smaller craft as efficient, and there definitely isn't space for 160 different providers. Okay, finally, let's talk about timelines. It takes a long time to do anything in space, particularly if it's new. And startups really, really struggle because space is very high investment and it takes a long time to get a return. Which means that venture capital tends to be from younger, more inexperienced players who get bought on the hype of, oh, wouldn't it be great if we could do X in space? And they don't realize quite how long it takes to deliver. I mean, many people have been burned. Most famously, probably in the UK, OneWeb, which had a £500 million government bailout, trying to do what Starlink was doing in the US of providing internet. And it's a genuine, important need that has a business case behind it. But the fact it takes so long means it's very hard to deliver it before you run out of money or the investors stop trusting you. So that's just 14 of the challenges of working in space. Right, so we've done a little bit on some of the constraints faced in the space sector. Let's talk a little bit about how we'd actually use these in anger, what the implementation are. And I'm going to skip over the next few slides because I've already covered this. So we're going to do some design. What we'll do is we're going to design a CubeSat together, or at least some of a CubeSat. And what we'll try and do is we'll try and focus on some of the engineering challenges involved rather than just the high level stuff. So this is the CubeSat we're going to be building. It's the bus framework for 3 of our recent satellites. So we'll just go through a few of the components, and there's quite a few things I'm going to have to leave out because they're under NDA or they're customer payloads. But hopefully it'll give you a flavor for the sort of things that go into a CubeSat or into a nanosatellite or into a microsatellite, and give an idea of where the challenges lie from an engineering point of view. So the first thing up is the structure, and it's pretty boring. Like, it's an aluminium box because aluminium's got great strength to weight. People have looked at composites, but it's yet to hit the mainstream for technical reasons. The main reason being that no one's yet pitched a composite with a 200-degree temperature range. If you've got one in mind, give me a shout. Yes, there's a very lucrative business opportunity there, but temperature being the killer again. In fact, the most interesting thing is if you look at this box, is the circled part. So these are rails. So this is what runs in what's called a tabbed deployer. So there's these 2 rails in a box. The structure gets put inside the satellite in it, obviously. And then when the rocket gets to the desired point, it releases the door on the box and the structure gets kicked out along those rails. A satellite has batteries in it, but I'm a software engineer. I don't find batteries interesting, so we'll skip those. Um, it also has radios. Now, there's a ton of different radio types we can use, but for this one, we're going to use an S-band radio, which is in the 2.3 gigahertz, and they're easy enough to make relatively omnidirectional. So the nice thing about that is that a satellite spends some of its most critical hours tumbling around. We'll come back to why in a bit, but you want a radio that's closest to omnidirectional as possible. Now, the downside of it being omnidirectional is it loses power extremely fast. So S-band tends to be on the lower end of speed for modern nanosatellites. And because Amazon sells everything, they also sell a ground station for this. You only need to put the um, S-band on your satellite, and actually you can just log into an online portal, not too dissimilar from the cloud, and just download your data. Okay, it requires quite a bit of programming and stuff, but it's relatively easy to get data on and off a satellite. Um, and then there's X-band. Now, so X-band, particularly on this mission anyway, is a much narrower field of view. So it only works when the satellite is now pointing correctly. And X-bands are quite a lot harder to work with because in the UK and a number of other countries, it's almost entirely reserved for the military, which means if you try and test it, guys turn up in tanks outside. Um, so you are limited in what you can do with it. But it is much faster. In fact, if you look at Starlinks, that's the ones that are currently ruining the night sky. Those ones are, those use KU band, which is not far from X-band. And someone in chat says, looks like GenMat 1, NoClip 1, and Moxie 1. You may very well be right. Another thing that goes into a satellite that may surprise you is quite the amount of wiring. It took Maxime, who's our wiring wizard, 150 hours to make the wiring for one satellite. And that's with most of them being pre-built. Now, that's something we've massively worked on because wires are one of the main causes of failure. We spent huge quantities of time testing every individual component, but to streamline future builds, we will definitely be reducing the wiring by, stuff. And one thing we've done is parallel assembly, and as a chat quite rightly pointed out, is that yes, we've actually built 3 of these things in parallel. They're quite similar. They have different payloads, but they're largely similar. And that parallelization is good because it means that the majority of the critical components in a satellite are identical. And bringing back to flight heritage. Flight heritage is really important. You want one design that works, and then you reuse it. So we're going to play a little pop quiz, which is when your satellite first gets kicked out of the rocket, it's spinning. So answers in chat, please. How do you stop it spinning? Any thoughts? You're a lonely satellite floating in the void. How would you stop it spinning? Well, I'll tell you what we'll do. Propulsion system. You are well. Come back to the propulsion system. Gyros. Okay, we're on something with gyros. Okay, that's all good. All good suggestions so far. So what we'll do is we'll quickly whip through some of the things you can do. You would normally only do some, and then we'll whip through some things that, So first up, question is, what can we measure? Your satellite floating in the void. You don't have the ability to know which way up and down is from gravity. So what can you measure? And then the second question is, what can we do with it? Star alignment. That's also good. We'll come to that in a second. So the overall system that works out how a satellite is spinning and then corrects for that is what we could call an ADCS, or attitude determination and control system. And the inputs to this system are power and data, and the outputs are hopefully spacecraft dynamics and the spacecraft spinning around. And typically what we do is we then split this into 2 parts. There's an ADS, i.e. the bit that works out where you are currently and which way you're pointing, and then the ACS, which is the bit that then fixes that. So first up, ADS, and we've already got some of these. So someone mentioned a gyro. Gyros are very high on the list. Now, gyros drift over time, so you can't use a gyro or an IMU to work out exactly which way you're spinning, so which way you're pointing, but you can use it to work out how you've changed in your pointing recently. So you can work out how much you're spinning around, even if you can't work out which way you're currently facing. And then there's what's called sun sensors. So sun sensors detect where the sun is, obviously. And then they can, if you know what your time is on board, then you can work out some of the directions. There's GPS, we'll come back to this in a second. Horizon sensors, star trackers, and magnetometers. So first up is gyros. I must confess they're boring. Everyone's got them. I don't have anything interesting to say about gyros, so have a picture of my neighbor's dog instead. GPS. GPS is amazing. It solves so many problems. It gives you position incredibly accurate. At 5 miles a second, you can know the position of a satellite under a meter, which is phenomenal. It's also got some interesting challenges, one of which is COCOM limits. So built into GPS when it was designed was the idea that people didn't want to be able to use GPS for, let's say, other countries wanted to build a missile or something. So when North Korea fires a missile, it can't use GPS, and the reason is it's locked away by the US. At least that's the theory. But while some of the restrictions have been lifted on that over the years, it means if you want to build a satellite, you'll actually have to spend a very large amount of money and time trying to get that special GPS that can operate at 5 miles a second without it shutting down. In fact, you'll find if you turn your GPS on in the plane, depending on the plane and the phone, you'll find your GPS may well shut down. Also, GPS, as this is just a complete random aside, I think it's quite cool, is there's quite a bit of evidence that GPS may be able to work on the moon. I love this diagram from NASA because it very helpfully decided to label the diagram as not to scale, as though somehow someone might think there was this giant Earth-sized satellite pointing down onto us. But there's quite a bit of evidence that GPS will be able to work on the moon because the side lobes from GPS satellites should intersect there, which I think is great because I can't get GPS to work on the subway, but it might well work 250,000 miles away from the Earth in the other direction. So next up is a magnetometer. So a magnetometer uses the Earth's magnetic field. It's basically a compass on steroids. And I think people don't realize how much the Earth's magnetic field varies, but this is a map. It's actually incredibly inaccurate. Now, if you've got really good timings and a really good model, you can actually get position out of this. You track the satellite's position over time, and you compare that to the change in magnetic field direction, and then you can use some orbital dynamics to work out not only which way you're pointing, but sometimes your position. And I don't think anyone uses this at all now because there's much better techniques available, but it's a really interesting idea. So there we are. Possibly one that's less obvious is a horizon sensor. So a horizon sensor is effectively a line scan thermal camera. And it tries to find the warm edge of the Earth against the colder space. You have one of these on 3 or 4 sides, and then you can work out where you are. One of the nice things about horizon sensors is it's very difficult to mess up. And they're very, very stable for technical reasons, but they also tend to be a lot more expensive than sun sensors. So this is a sun sensor. We have one on each side of the satellite, and they've also got a quad pole diode in it, but that doesn't really matter. And the sun comes and hits all of them, and then you can use the ratios between which ones it's hitting to get a pretty good estimate of where the sun is, typically about 1 degree for this particular make. And then next up is star trackers. Now, star tracker, so if GPS is the gold standard of position, star tracker is the gold standard in pointing. Star tracker can tell to an incredible degree of accuracy which way you're pointing. The downsides are it doesn't work when you're spinning fast, and it's quite computationally intense. In fact, if you put this picture into a star tracker, you could work out where you were. Question from chat: are you using a more accurate version of GPS called Galileo? Yes. In fact, GPS is like Google was a term. Everyone uses GPS. when they actually mean GNSS, and that's normally GPS Galileo and one or more other systems as well nationally. Um, and the only reason I'm showing you this picture is because it's a star tracker that we built. I spent a large fraction of my life programming it, and I don't want that wasted, but it's got no relevance to talk. So the way a star tracker works is actually really interesting from the maths point of view. It's constellation mapping. So you take a picture of the sky, you try and find the brightest stars in your picture, normally about 5, and then you try and match it to your constellation diagram. Now that's quite hard to do. It's a really interesting challenge, particularly if you're trying to do it on a very low power computer that has to be extremely reliable, and your camera may clip the edge of the sun, so it will saturate suddenly. So it's quite a difficult challenge, but it's very interesting. You can do some really cool stuff with this. You can do role estimation, and yes, you can work. You can star trackers are the gold standard for pointing. So, quick summary of what we've got for working out where we are, where we're looking, but we can't do anything about it yet. So the first is gyros. Obviously, they've got no knowledge of where you are, but they've got a decent understanding of which way you're looking. GPS has amazing position, but no pointing. Magnetometer has next to no position, but some pointing. Horizon's sensors have no position, but good pointing. Sun sensors the same, and the star trackers have fantastic pointing. Now, the reality is until GPS came along, almost everything you did for attitude determination was through triangulation of 2 pointings. For example, you might take a star tracker vector and try and intersect that with a sun tracking vector. And then you'd integrate that over a period of time, and then you'd use your knowledge of orbital dynamics to work out where you were. With GPS, the job becomes a lot easier. So, next up, once we know where we are, how do we correct it? So the first response people always say to this is thrusters. And the answer is that no, actually, thrusters are rarely used for correcting spin. There's a lot. I'll come on to the reasons why in a second. Instead, the 2 big ones are what we'd call magnetorquers and reaction wheels. So, why do we use thrusters? Well, the first thing is they're expensive. They have a limited fuel supply, and they can cost as much as the rest of a satellite put together. They're very, very high tech things, and they're also very high risk. But the biggest thing is they're actually very slow. Their response times are far slower than you need if you're going to try and correct the spin of a satellite. And your fuel runs out. And you normally see if you're going to spend the money for putting chemical thrusters on a satellite, you would typically want to use that for orbit changes. Electric thrusters are a bit more flexible. So these operate in many, many different ways, but typically it's by some variation of using solar panels to collect power, then using that power to create an electric field, and using that electric field to accelerate heavy ions out the back. And they can be incredibly efficient. There was some news articles this week about MIT having made the most efficient thruster ever. Now, the issue is they've got very low overall thrust. So if you put one of these in space and you run it for 1,000 years, you could go faster than anything else, but you can't get out of Earth's orbit with them, or at least not currently. And again, low thrust, slow responses means they don't really work that well for correction. Instead, what people typically use is a magnetorquer. So this is typically the bulk tool. A magnetorquer works by putting an alternating current for a coil, and then as you'll know from physics, that will react against the Earth's magnetic field. And if you run it at the right frequency, you can effectively slow the spin of the satellite relative to Earth's magnetic field. Now, you can't stop the satellite spinning around the field lines, but as you would typically travel around in a non-circular orbit anyway, you can normally get rid of most of the momentum of the satellite with this. And with some very clever orbital dynamics, you could completely break a satellite's roll. But the precision element that people use is what's called a reaction wheel. So reaction wheels are a gyroscope again, but gyroscopes like we would have had at school, where you pulled a string and they spun on the end of the top. You put energy into the wheels and you spin it up, and obviously the satellite then spins in the other direction. Reaction wheels have the disadvantages: they're expensive. You don't want moving parts in space, if at all possible, and they've only got a limited capacity. You can run them up to say 10,000 RPM, and then you have to find a way of getting rid of that energy again. So normally what we end up with is some combination of magnetorquers and reaction wheels to control the spinning. And then if we do need to change orbit, we'd use either chemical or electric thrusters. So bring it all together. So in the satellites we're building, this is what we've done. We have an ADCS, we have reaction wheels, sun sensors, magnetometers, GPS, and a star tracker. For future projects, I've definitely got more options, but this is one of the cheaper ways to get a really reliable system without having to put in lots of expensive components that then use high power and take up lots of space and then delay the amount of time it takes to deliver a mission. So I can tell you that when we ship these, you will not believe how much our insurance bill tanked. It made life a lot less stressful. And you then mount them into a deployer. So the picture on the right, there's two different missions here, I'm afraid, but go in a deployer, and then eventually they'll go inside a rocket. This isn't from our mission. Currently, our satellites are somewhere in the US waiting for their mission slot to go. So hopefully that's been an interesting insight into some of the things that go into a satellite and how they work. And I realize it's been a really whistle-stop tour. There's a lot of stuff I haven't said. There's a lot of stuff I have skipped over. In a second, we'll have another round of opportunities for questions. But first, I want to give you a quick insight into what we're trying to do as a company. Because as a company, we're doing satellite builds. We make subsystems. We make ground support equipment. We've got 4 missions due to fly in the next couple of months. 3 to low Earth orbit and 1 to lunar orbit. In fact, this is possibly the one you may have heard of, which is Doge 1. About 2 years ago, there was a lot of stuff on the news about someone having paid for a mission in Dogecoin. Well, that's this. We're not the company that bought the mission, but we are the company that's building it. And that is Doge as in the meme. And we're building it for a company called Geometric in the US. But our long-term goal as a company is to do deep space. So I was asked earlier about what's our pitch as a company, what makes us different. Well, a big part of what makes us different is we're trying to lay the groundwork for being able to do commercial space, and commercial space run commercially as opposed to commercial space paid for indirectly by NASA. And what we want to do is we want to head to the moon, which reminds me of the old joke that faking the moon landing properly was so difficult that they ended up having to film on location. So that's our aim. We want to film on location. And to do that, we've been building satellites that are, as far as we can, rated for the additional challenges of working on the moon. And then over time, we'll build them into integrated lunar compatible systems. And eventually, hopefully, in not too many years' time, you'll be able to buy a lunar roving mission from us. But though that's big picture, long term. But to do that, we have to face some interesting technical challenges. And there's a lot of open things here that if anyone on this call has some ideas on, I'd be very interested to know. Because while low Earth orbit is really well understood, the moon has some unique challenges. There's radiation, it's much, much worse. Mass constraints are much, much worse. We're talking 10 times the cost at least. Temperature can vary between plus 150 to minus 200. The magnetic field, there's no magnetic field on the moon, which actually means there's a huge quantity of stuff you can't do on the moon that you might want to do. And finally, comms. There is currently no technology on Earth that could stream a 4K video to Earth from the moon. Again, that may be changing, but there's nothing that can currently do it. And there's a lot of companies that have been paid by NASA to develop lunar landers as one-offs. And we're keen to be part of that. And our focus is on to building stuff suitable for deep space while also commercially viable for operation in Earth's orbit. And with that, and ask questions. Thank you very much.